So this is natural logarithms. We're still in section 9. But it's not a particular topic. These are my own notes, not from an Algebra Nation video, just like the last class. Okay? All right, so we talked about Euler's number the other day. Remember we did that lesson? Euler's number is that irrational number. It's approximately 2.71828, right? So today we're going to talk about what happens when you have a logarithm and the base is Euler's number, okay? When that happens, these are called natural logarithms. So, natural base exponential functions. What's that? Oh, forgot to target. Let's do target. How about that? Thank you. How do you solve a natural logarithm question mark? What is meant by a natural logarithm? How do you solve a natural logarithm, and what is meant by a natural logarithm? All right. Now, natural base exponential functions are exponential functions with base e. And we know when we see that little cursive lowercase e, that is Euler's number, represents approximately 2.71828, right? So we're going to write that down. E, or Euler's number, is a common irrational number that is approximately 2.71828. Natural base functions are useful for describing continuous growth or continuous decay. Exponential functions with base e have the same properties as other exponential functions. So remember the other day we did that continuously compounded interest problem, where you had the amount in the account after t years, and then you started with your initial amount, which is called the principal, times e raised up to the r times t, the rate times time. And we'll have another one of those today, but one that we'll have to solve using what we know about logarithms. All right, the exponential function y equals e to the x. Has an inverse. Comma, the natural logarithmic function. So the exponential function is y equals e to the x. We know the inverse, we flip-flop the x and the y, right? So the natural logarithmic function, if we flip-flop the x and the y, we would have x equals e to the y, which is log base e of x equals y. When the base of a logarithm is e, we call it a natural logarithm. Do y'all remember the other day when you had a base of 10, we called it something special? What was it called? Common logarithm, right? So if you have a base of 10, it has a special name, common logarithm. If you have a base of e, it has a special name, natural logarithm. Okay, everything else, just a regular old logarithm. So when the base of a logarithm is e, we call it a natural logarithm. And instead of writing log base e, we just write ln. So, log base e of x equals y is the same as the natural log of x equals y. So if you have a base of e, they're not going to write it log base e, okay? They write it with ln. On the calculator, remember the other day when we wanted to do e to the x and it was above that key that said ln? That's the natural log. So if you're taking the natural log of something, you just push the natural log button, okay? So that's what that means. It looks weird. Why do they have to write it weird? Why can't they just write it log base e? I don't know, but that's what you're going to see. The natural log of x equals y. That just means a logarithm with a base of e, okay? Yes? Say it again. ln x equals y. So ln means natural log. That means a logarithm with a base of e. So the natural log of x equals y. That's how you say that. Okay? And I know I just pointed this out, but I want to write it down. There is so natural log, this is what it looks like, key on your calculator. All right, so now we have all those words written down. Let me show you how to solve equations that have natural logarithms in them. Okay? So this is called solving an exponential equation. And the good thing is you pretty much do it the same way you solve any other exponential equations when you need a logarithm. It's just you're going to have a base of e. So first example, we have e raised up to the x minus 2, and that equals 12. Okay, if that was 5 raised up to the x minus 2 equals 12, and we wanted to solve that, well, first of all, do you think we could write both sides with the same base? Probably not. So if we can't write both sides with the same base, what other way do we know? Say it again. Right, we put it in logarithmic form, right? So it's currently in exponential form, so we'll just convert it to logarithmic form. So logarithmic form, that would be log base what? E of 12 equals x minus 2. But I just told you when your logarithm has a base of e, you don't write it like that, right? But here at the first part, I wanted to do it that way, so when you're going back through your notes, like, what is this? So yes, we wouldn't write log base e of 12. We would say the natural log of 12 equals x minus 2. Now, if that would have been log base 4 of 12, could we have evaluated log base 4 of 12 in the calculator? We could, right? But this is the natural log of 12. So what do you think you put in your calculator? 12, if you're using the TI-30XA, you're going to put the 12 in first. You know how it's backwards than most other calculators. And then you'll hit the natural log button. And so the natural log of 12 is approximately, let's go with 2.48. And you might want to make yourself a little note that we evaluated the natural log of 12 in the calculator. So probably any other calculator you would hit the natural log button first, then 12. But these, everything's backward. 12 natural log. What do you think we do from here? Yeah, add 2 to both sides. And x is a oops, didn't mean to do that. Didn't mean to do that either. Try it again. X is, I rounded 2.48, so I'm going to say approximately 2.48 plus 2. It's approximately 4.48. So if we wanted to check that, if x is 4.48 minus 2, that's 2.48, right? In our calculator, we could do e raised to the 2.48, but remember we rounded that. So 2.48 second e to the x is 11.94. It's supposed to be 12, but didn't we round that number? We rounded it to the hundredths place. So if we would have kept going, it would have been more closer to 12, right? So I'm going to say it's probably correct. Coolio? All right, let's look at this next example. We have 2e raised to the negative x equals 20. Okay, so can we write both sides with the same base? No. All right. Is this in exponential form? Not yet. What do we need to do to get it in exponential form? Divide by 2. Very good. And a lot of times students forget that part and they're like, this isn't working out right. What's wrong? So make yourself a little note that this is not in exponential form. That e needs to be isolated first before we can convert it to logarithmic form. So that would give us e raised to the negative x equals 10. Now don't worry about, oh, but the exponent's negative. Don't worry about that just yet. Let's put it in logarithmic form and see what we have there. Okay, so logarithmic form, natural log of e, what do we write? ln, right? That means the natural log base e, of what number? Equals negative x. Now can that value that's in y's space, can it be negative? Yes. B can't be negative, the base, and what's in x's spot can't be negative. Okay, so our base is e, what's in x's spot is 10, those can't be negative. What it's set equal to on the other side, that can be negative. Pretty much. Yeah. All right, so what are we going to do now? The natural log of 10, right? So in this calculator, I'll do 10 natural log, and you don't have to push, I'm just used to pushing equals, but you don't have to when you put that in. So let's go with 2.3 approximately equals negative x. Is that my answer? What do I got to do? Divide by negative 1. So x is approximately 2.3. Coolio? Negative 2.3, yes. You know what I meant? Negative 2.3. All right, let's look at this one. Anybody have a question on that? Okay, e raised to the 3x, and then I have a plus 5 that's not in the exponent, equals 15. Yep, I'll subtract 5 from both sides because it's not in what? Exponential form. And we cannot convert it to logarithmic form until it's in exponential form. So that's e raised to the 3x equals 10. Now what shall we do? Logarithmic form, so it'll be log base what? What? Log base, what'd you say? Natural logarithmic form. So log base e is the same thing as the natural log, right? Of 10 equals 3x. I'm sorry, I couldn't hear you over the air conditioner. Now what will we do? Right, figure out what the natural log of 10 is in our calculator. So we have 10 natural log, and that's approximately 2.3. Of course, the closer, if you round, you know, to the hundredths or thousandths place, your answer is going to be more precise than the tenths place. Then we're going to do what? Divide by 3. Bless you. And x is approximately 77 hundredths, is that right? Yes. And then of course, if your directions told you to round to a specific number, then that's what I would round to. All right, y'all wanna try one on your own? So we'll try one on our own, then I got a little word problem, and then that'll be it for the notes. Unless you feel like you need more practice. All right, we have 4e raised to the 2x. Now is 4 being raised to the 2x or just e? Just e. And then plus 2, that's not an exponent, set that equal to 16. Solve that one on your own. Anybody come up with the answer? Raise your hand if you got it. Millie. Say it again. 0.35. Anybody get anything different? What'd you? 0.2345? 0.345? What'd you get? 0.63? Anybody get something different? 0.63? I got 0.63. Okay, so let's see where we went wrong. Okay, what should we do first? Subtract 2. Let's do that before anything else. So 4e raised to the 2x equals 14. Then what? Divide by 4. This is not logarithmic form with that e there, right? I mean with the 4 there, with the e. So e raised to the 2x equals 14 divided by 4 is 3 5/10. Now is it in logarithmic form? Yes. So the base is going to be e. Log base e is a natural logarithm. So the natural log of 3.5 equals 2x. Okay? Am I going to divide by 2 right now? No, let's figure out what the natural log of 3.5 is, or 3 5/10. So 3 5/10, take the natural log of that, and we get approximately 1.25 equals 2x. Now what? Divide by 2. And x is approximately, when I divided by 2, I got this number, which I'll round to 63/100. If you didn't get that the first time, do you see where you went wrong? My colors don't show up on there. Does anybody have a question? The blue doesn't show up, does it? All right. We all good? All right, word problem. If you took financial algebra last year, you've probably seen this word problem many times. OMG, I don't have my microphone plugged into the computer. This probably isn't even recording correctly. We'll see. All right, if you deposited $3,000, into an account earning 5% annual interest, compounded continuously, comma. Compounded continuously is important because that's a different formula than if it's compounded quarterly or annually or monthly or whatever. How many years would it take to earn $10,000? So remember, we did this formula the other day. When it's compounded continuously, the formula is A of t equals P times E raised to the RT. Y'all remember what A of t represented? Amount in the account after 2 years. So you've invested it for 10 years, you started with 4,000, how much do you have after that? So this is just one number that goes here, okay? That's function notation. Think about it if it was a y equals, okay? It's just one number. So that's the amount in the account after t years. What did P represent? The start, which is when you're talking about money, how much you deposited initially, that's called the principal, okay? We know E is Euler's number. That's not a variable. You're not substituting any number you want in for E. E is 2.71828 approximately. What does R represent? The rate written as a decimal. So, whoops, I don't want that color. Yes, in decimal form. So for 5%, what would we write? 0.05 or 0.05, either or, okay? So R is rate in decimal form. And T is what? Time in years. So if they said in 6 months, you would have to convert that to time in years, okay? If you put in a 6 for 6 months, that means 6 years. So amount in the account after 2 years equals the principal amount times Euler's number raised to the rate times time. So this problem said, if you deposited $3,000 into an account earning 5% annual interest compounded continuously, because we use the E, that's the formula for compounded continuously, okay? How many years would it take to earn $10,000? So which variable do we not know? T, right? We don't know time. Well, what would we write? What would we put for A of T? 10,000, because that's how much was earned after however many years. We don't know how many years it took to get 10,000. That's what we're trying to find. So what would the principal be? 3,000 times E. We don't substitute anything in for E. Raised to the rate. The rate is 5%. So what are we going to write again? 0.05 or 0.05 times the time. Do we know the time? No, that's what we're trying to find. How long would it take to get $10,000 if I deposited $3,000 earning 5% interest compounded continuously? All right? So our variable's in the exponent. This is the whole reason we learn logarithms. All right? You need to know how to do logarithms for when you have a variable in the exponent. All right? Any other equation we ever solve doesn't have a variable in the exponent, right? But logarithms do. So 0.05 times t, isn't that just 0.05 t? Okay, so let me write that. 10,000, because usually we multiply those together, they give us two numbers. Well, they didn't. We have a number and a variable, that's fine. So E is raised to the 0.05 t. Well, doesn't this look like an exponential equation? Right? It's not an exponential form yet, but could we get it in exponential form? What would we do? Divide by 3,000. So 10,000 divided by 3,000 is approximately 3.333 equals E raised to the 0.05 t. Say it again. Oh, that's my multiplication symbol. I use that because I had that decimal and I didn't want that to look like another decimal. So it was like, instead of putting a dot, I put a X. So it's not an X, it's like multiply. All right, is this an exponential form? Yes, can we write it in logarithmic form? Yeah, what would be the base? No, E, right? It's flipped on the other side, but the base is always whatever has the exponent with it, right? So instead of log base E, we're going to write natural log of 3.333 equals 0.05 t or 5/100 t. Now we already know at this point, we can evaluate the natural log of 3.33 in the calculator. And that's approximately 1.204, I'll say. And then I'll just divide by 5/100. And t is approximately 24.077 years. So it's going to take, the question said how many years would it take to earn 10,000? So when you turn to the 24th year, you're not going to have $10,000 as soon as the 24th year starts, right? Sometime in the 24th year. So if it's whole years, you'd have to say in the 25th year. All right, so it kind of just depends on exactly how they're answering it. I'm going to say it would take almost 25 years. is if you say 24, when you start the 24th year, you're not going to have $10,000 yet. Coolio? And that's that. Like I said, I did not plug my microphone in, so I don't know if my laptop's picking up the sound or not. If it is, then I'll post this video and embed them into the notes in the Teams. If not, I'll record it in my next class that doesn't. Try this again. All right? Anybody have a question?